All right, folks. Welcome back to Advanced Track. Today, we're done with the guided project. So the next two sessions, specifically this week and the week after Thanksgiving, so week 9, we're going to be talking about kind of more modern methods of machine learning. And today we're going to be starting with a lot of methods that are in natural language processing and time series data analysis, which is not something that we have really talked about a lot so far. But I think this is this is also a very, very important workshop because you're going to see kind of like the other side. We've been dealing with, classification problems a lot. We have been dealing with, we have one image, data distribution, just a bunch of images, but sometimes that's not what your data looks like. Real world data is a lot more complex, has time series data to it, you have sequential data, and this is what this workshop is for. We're going to introduce you to embeddings, which is the idea of capturing kind of like words and words or just images or anything with mathematical objects, vectors, RNNs, or recurrent neural networks, which allows us to process time series data, LSTMs, which is just basically a fancier method for recurrent neural networks, and finally transformers, which is what powers a lot of large language models, including ChatGPT today, and also is seen almost everywhere now for any remotely large foundational model and generative model. So without further ado, let's get started. Of course, the asset cluster is still in the same link. You can find the slides there. We have a few slides that are hidden because we're like, time constraints. So if you want to see more details, you can always see the hidden slides. So let's get started with embeddings.
Okay. All right. So, well, welcome. All right. So the first question that a lot of you might be having is, how on earth can we represent words as something that a machine could use? Could you take the ASCII values? You could, but that gets really complicated really fast. So example problems that we need to consider. So the baseball player ran over to catch the ball, or the grizzly bear went over to catch the fish. So what are so obviously these are the most obvious logical answers to these sentences, but something to think about is what clues did we use, and also how much context did we need? So we know that in baseball there's a ball, and grizzly bears, they love fish, so that's the context we need there. But how do we train this into a computer? So one naive approach is to simply just count the number of occurrences of each word and go from there. So this is called a bag of words model. So it says, I love this movie, it's sweet, but with satirical humor. And then we just kind of count all these words. It comes up a lot, I, the, to, and blah, 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 blah. But this isn't very great at capturing context. So Houston, we have wow, this presentation is bad, not good. But it's also good, not bad. Which is it? See, we know because we understand the context, but a bag of words model would see basically no difference between these two. So it can't tell, is it good or is it bad? You never know. So the key is there's no context. So obviously, as the meme here, they're the same bag of words as the picture says here. So, and here's another example. It's even more subtle. Let's eat grandma, and then let's eat grandma. I don't know about that. Unless you're crazy, I don't think I would exactly enjoy the second one. The first one, I guess it also depends on what you think of your grandma, but besides that, but that's besides the point here. The point is both of these are really similar sentences, and very slight bits of context change the meaning significantly. So, yeah, I don't know who that, I feel like that, I don't know. Okay, yeah, English teachers going to town, computers getting F's in the class. So let's talk about a way we can solve this problem. Introducing embeddings. So embeddings are a way of basically capturing relationships between words. So for example, we can take father and we can say they can have a child, and it could be a son or I don't know why these two are like mixed up like that, but whatever the case may be, they could have a boy or girl, son or daughter. And then you could say like the male parent is the father, and so that kind of information is what embeddings hope to capture. So other examples here: Paris is the capital of France, Tokyo is the capital of Japan, so on and so forth. Now, so the idea is to generate vector encodings to capture words in our vocab that would have relationships to other words. So to give you an idea, here's the vector for king, here's the vector for man, and here's the vector for woman. So what do you think king minus man plus woman would be? If you thought queen, congratulations, you're right. And this is a good example to show just how important context is. And so with word embeddings, we can capture this information and we can find these kinds of relationships between words. And then we can train this information. We can feed this information to computers for RNNs, LSTMs, and transformers. So one of the ways we do this is a technology called word-to-vec, which is essentially, one of the more basic sort of like ways that you can transform a word into a vector, and it captures relationships. I don't know if y'all have played the game Semantle. It's a game where it's like you have to guess the word based on its semantic similarity to other words, and Semantle is powered by word-to-vec. So, and then here are some other ways that we can use word embeddings. So we have the sentence, I have failed at times. So we have, I have blank at times, cbow here. It works to, it computes the sum, gives us a function, and we get failed. And we can also insert it into, we can insert a blank word into a sentence like skipgram does here. So, and to show you just how, to give you an idea of how this works with matrices, we use a technology called one-hot encoding. I forget if we did we cover one-hot encoding?
I don't think we have, but sort of. So does anyone remember, I think I mentioned it like once, does anyone remember what a one-hot encoding is? Okay, so it's basically a method to burn, let's say you have like 10 objects, right? 10 classes of things that you want to represent distinctly. You can, with these 10 things, you can say represent them with, the first object is the number 1, the second object is number 2, and so on and so forth. You can do that, but the issue is the more objects you have, the larger the magnitude of that thing is. So instead of doing that, what we use is something called a one-hot vector. And what a one-hot vector is basically if we have 1, 0, 0, 0, 0, that's our first object. That corresponds to our first object. 0, 1, 0, 0, 0 corresponds to our second object. It's basically a vector that's all zeros besides a 1 in the object that we want to represent. If you remember for like multi-class classification, this is what we want our output to be, right? Our output vector, if say we want, if the fourth class say is cat and we want our model to be cat, we will want our model to output something like 0, 0, 1, 0, 1, 0. So that's what one-hot encoding is, and it's convenient because it is a much better way for us to, and normalized way for us to represent categorical data. And in the case of words, where you have distinct words all the way from each other, if you can imagine each of them as a separate category, that's why we use something called like one-hot encoding. In this specific case, the one-hot vector is really just there, so we can't say if you have 0, 0, 1, 0, 0, 0, 0, 1, 0. This, when you do matrix multiplication, if you think like kind of applying like this, will basically zero out every single thing here and only keep this row. So we're basically just only extracting this row. So we're basically saying 0 plus 0 plus 0 plus 1 plus 0, because every single other thing here is going to be multiplied by 0. This is just a nice mathematical trick for us to extract a row in a matrix.
Yeah, so obviously, as Jordan said, obviously because it's the fourth, element in this one-hot vector, we get the fourth row here, and then that's our output. And so that's all fine and dandy. But then sometimes we also get sentences. Now, and the question that arises there is, how do we break down sentences into words? and also, and there are many ways to do that. So, and the way we do it is with tokenization. So we basically cut a sentence into bite-sized pieces, but the exact way we cut it can vary drastically. So I love pizza becomes I love pizza. That's like the easiest. That's like the most. That's that's like basically one of the. That's just one way of doing tokenization. Is that you separate the spaces and say that that's a discrete word. But there are also other ways. So we can do word tokenization. I love coding, but we can also do character tokenization, which include love becomes LOVE. But we could also do subword tokenization, such as chat and ting becomes obviously chatting. This can be useful with words such as like a word like inexcusable. The word in is a prefix and it has meaning in and of itself. So just separating by words is often not enough. So this is why we have these different ways of tokenizing. And we can also obviously sentence tokenize, separate sentences. So if you have a paragraph, you can do sentence. And then a sentence can go into words and so on. Another way we can do it though is with a technology called byte pair. So if we have like AA, we see that occurs 4 times. And then we have AB, which is twice, so on and so on. And this is actually the technology that ChatGPT uses, right? Byte pair, I think.
I think so.
Yeah. So basically, yeah, ChatGPT. Yeah, I mean, I actually just learned this yesterday. This is how I didn't even know this, but ChatGPT uses this method of tokenizing. And if you want to learn more about it, we have a link in the slides here. Yeah, so here are obviously several different ways of cutting pizza, the way we can cut up paragraphs of text. But so here's a tricky example though. The word aren't. It's one word, but it's really 2. So do we cut it here? Do we cut it here? What do we do? So obviously we have a couple different options there. Now and obviously this is something you really don't want to do because it just doesn't make any sense. There's 2 kinis. I don't know what that's even supposed to mean, at an ion. If you can try to make sense of that, I applaud you, but I don't think I can't. So obviously there are trade-offs with each different kind of tokenization. So if we do word tokenization, we get a shorter sequence, which means not as much data. But that's also good because it might be quicker to train. However, if we do character tokenization, we have more complete information, but we also have a longer sequence, which again has more information, but it's also much more time-consuming to train. And now, with that out of the way, with embeddings and tokenizations, we're now going to talk briefly about the motivations for RNNs.
Okay. Real quick.
Yeah.
So if you go back to the embeddings, I think one thing that we could maybe made a little clearer is how exactly we're training these embeddings. Is like, okay, we found these vectors that allows us to that represents the meaning of these words in the English language, but how do we actually get there? And there have been many methods proposed on how we actually would train or like find these embeddings corresponding to words. And generally the most accepted way is just to say, we look at a really large corpus, which is just the NLP term for really large amounts of text, right? Say they may train this on, say, all the Wikipedia articles and stuff like that, right? You have this really large amount of text, and first what you would do is you would extract all the unique words from the text. And you may do other things like lematizations, which is the idea of like turning text, like the word birds and bird are actually the same word, so you remove the S and stuff like that. Then what you will do is you basically create a one-to-one mapping between all your words with each with a randomly initialized vector, right? And what we want to do is basically the randomly initialized vectors are our weights. These are the weights that we want to train so that we can use them to do some sort of prediction. And specifically what we'll be doing, for example, one of the ways you can do it is you look at, in your data set of a bunch of text, you look at a sentence and basically go, okay, I'm going to say randomly mask out some of these words. And and this sequence of words, I'm going to feed into some sort of neural network, which we actually will talk about. RNNs, LSTMs are actually one of the networks that we will use. But we feed these randomly initialized, the initial embeddings, the embeddings that we have randomly initialized, we feed them into our network and we try to predict what are the output words which are here, right? And basically what we do is, as we're training our model to do this sort of prediction, if it gets good at predicting what words should go between two words, it necessarily has to start sort of understanding the relationships between words. So we just keep doing this, we will get two things. First, we will train out a really, really good model that will be able to fill in words. It's nice, but that's not what we're looking for. Most importantly, our embeddings in this case will start to get closer to encoding information of the words themselves. Because if, say, our embeddings did not encode information of the words themselves, then the neural network, which takes in these embeddings and actually does the prediction, will not be able to actually extract information. If our neural network is able to take these embeddings and actually be able to make this prediction, that means these embeddings themselves must contain some information about the meaning of these words. And and afterward, we have this list of embeddings that we just say, okay, that's our kind of like massive data set of corresponding English words to vectors. And we can use those vectors to train more downstream tasks, if that makes sense. So that's generally how people have been doing embeddings. And the idea of embeddings doesn't just stop at words. Like basically, a lot of times the way you would get embeddings is you basically train the model to do something that is really, really general, such as predicting what word you have accidentally masked off. And by being able to do this really, really general task, it will start to understand what your non-vector, non-mathematical like data set is and do this sort of correspondence. So that is what embeddings are, and that is why it is very useful, because after we have trained all these embeddings, we can then use them to, say, train a downstream model. And we say, okay, these embeddings have a lot of meaning, let's use them to train some model later. So that's the idea behind embeddings. Does that make sense? Kind of? Kind of. Okay.
So if you want like a visualization, then you can sort of look at this to get an idea. Can you guys over there see it? Sure. The idea is that if you have some vocabulary that your model knows, like it knows the word I am a very small model, knows those 6 words, then you can get a one-hot encoding of any given word. Then you pass it into some normal neural network. And the idea is that the output of this is going to be a probability distribution that tells you how related your given word is to every other word in the model. So how related is this one, this one, this one, this one, this one, and this one, right? And so we know what this is supposed to be from the text that we have. So we'll have like a corpus that has these 6 words in it and in various configurations, and that tells us how related they are. And from that, we can determine like what our weights and biases should be for our model. And so the embedding then is going to be this guy in the middle. That's the thing that we're learning. So whenever you look at the embedding for like the word vary, in this case, the embedding that we're going to be learning for in the end is going to be 827, because that's the value in this middle.
So the embedding for each maybe token is different.
Yes, exactly. And the size of your input and output vectors is the number of tokens that you know. So if your vocabulary is, say, 10,000, then your first and last vectors are going to be each 10,000, and then the middle vector will be something like, I don't know, 50, which is, I think, the size of word to vec. That's the size of the embedding.
How does the model learn how to tokenization?
The tokenization we covered earlier.
Yeah, I mean how the model like know where to cut the words.
Oh, I think that's something we determine, right? Like where.
Yeah.
Yeah.
Yeah. Like we determine, basically we choose how to cut the words.
Yeah.
Yeah. I mean.
It started out as because a lot of these are from like classical linguistics, right? It started out as like, oh, we can like parse them in certain ways and cut all words. And nowadays, like ChatGPT is like kind of statistics where you're like looking at a really, really large data set and just going, what are the most common token patterns? So how can you most efficiently kind of chunk them into like
prompt, and you have like, hundreds of thousands of tokens, or like different types of tokens, and it's like a entirely deterministic prompt. You're kind of learning something, but you're not really doing like weights and biases for learning. It's just, hey, let's look at this data set and let's like you may have heard of this like not hacking code, but like there are ways to like how zip compression works and zip tree and like stuff like that. You can like maybe or like biterial encoding. It's basically saying like let's look at the most commonly occurring like pairs of characters or pairs of ASCII values, and that's also why ChatGPT, because they're working with like symbols and stuff, it's able to generate also other languages, because instead of trying to formalize them into like English words, just saying that's a ASCII value that we're treating as like a token, and we just have to like map of like token pairs to like vectors that they train. It's very big, it's very like impractical to train on a laptop, but if you have a ton of GPUs and a ton of storage, this actually works relatively well.
Yeah. So obviously, now we're going to talk about the motivations for RNNs. So these are basically the types of neural networks that we're going to use. So all the neural networks that we've covered so far are called feed-forward neural networks, and the input is static. So whether it be the example that we've covered a lot obviously is images. So an image is one input, and so obviously it's static, and the input space is independent of other elements. So we have one image and then another, but it's not like a video necessarily, where that's an example of something that would be sequential, where because a video is divided into like many different frames, and so like the image, the next frame obviously depends on the previous one, and so on and so forth. So obviously that's a key point that we're getting at here is, do data samples always have to be independent of others? And the fact is, sometimes we don't want that. So we have input sequences. Obviously, here's an example of a video which covers a fall incident. So other sequences we could use are obviously, so we have audio, text, and so and the key is we get information about past input, and that can inform current predictions as a recurrence relation. So I don't know how many of you have taken Math 61, but if you might have covered recurrence relations in that, but basically each sequence or each element depends on the previous one, except for the base, really. And so and then we get like initial conditions there. So what are some other examples of sequential data? Obviously there's audio, text, video, so on and so forth. I can't really think of another one. Like a timeline, maybe, like someone.
Weather.
Oh yes, weather. That's a good. Yeah. Oh yeah, that's another good point. Like any like disease like case numbers, like obviously like if you have like if it's increasing, there's a good chance like the next one's gonna be higher than the previous one. So that.
Stop.
Oh yeah, stocks. I don't like. Yeah. Geez. Yeah. Obviously that there are many more that something that maybe we don't even know about yet. Like there are lots of pieces of sequential data here. So RNNs are a type of neural network that can handle this kind of data. And so it's used in speech recognition, language translation, video classification, so on and so forth. To actually talk about RNNs, Sparsh, right? All right, so Sparsh is going to talk about a little bit more about how RNNs actually work.
Yeah. Okay. So for neural networks, as we have talked about them so far, right? The format is you pass in some input layer, then you have some hidden layers, and then you have your output layer. And then you know what your output is supposed to be. So based on what it's supposed to be, you learn the values of the hidden layer, and then you keep passing in inputs until your model performs really well. So RNNs have a slightly different structure, which they have in order to make use of that recurrence relation property that we talked about just now, where you pass in not only your input, but also a layer from the previous iteration. So that would mean, for example, if you are passing in a word, right, and we're passing in, say, a word embedding, then we'll pass in a word embedding into our model. And then for the next word that we pass in, we're going to have not only our word influencing our model, but also something from the previous model that informs how this next iteration is going to run. And so when we pass in the next word, again, same thing. Something from the previous model, from the previous layer is going to inform how the next model runs. So it'll look something like this. That will be the general flow. And again, to differentiate this from normal models, the way that they will normally work is that you just have your input and it goes through hidden layers and produces an output. You pass in the next one, it does the same thing, right? There's no transference from one layer to the next, but here there is. So you can sort of see how that works, and then we'll get into a bit more detail about what exactly this means. Okay, so, and again, you can hopefully see how this unrolled version is the version that I just drew on the board. This rolled version is, I guess, a more accurate version of what exactly is going on under the hood. So now, if we look at this in a little bit more detail, what we'll see is that when we pass in an input, right, it's going to be some sort of vector. We're going to multiply it by a weight matrix, add in a bias, and pump it through a nonlinearity function, right? And we get a hidden layer value. So for the next time that we run our model in, this is going to influence it in the following way. We're going to pass in, say, perhaps weight times our input plus the previous hidden layer plus the bias. So as you can see, the value that we had here for our hidden layer is going to then be fed forward into the next part. And so we're going to keep doing this as we progress. So you can see that this is yet another weight matrix we have to learn, right? Not only do we have to be concerned about what our hidden layers are that we're learning, we also have to be concerned about the weights that are being applied so that we can get this value. And that corresponds to this W matrix here. These are the weights that we'll multiply this hidden layer by in order to get the next thing that we're going to feed back into the model for the next iteration. Okay. So far, does anyone have any questions about the structure of RNNs?
I have just a small question. Are there any weights also for the pre-hidden layer, or it's just like the weight is counted as with a new layer together?
So when you're calculating the previous hidden layer, what you're going to end up doing is that you're going to be spitting out two things. You're going to be spitting out something that's going to keep going through the model, and you're also going to be spitting out a second vector. And that second vector has weights, and you're going to need to has weights associated with it that generate that second vector. So you need to learn those weights in addition to the weights for the model. Okay. Yeah.
What if you have multiple hidden layers?
That would be a hyperparameter, so you can choose how far down the model you want to go. Typically, our RNNs only have like one hidden layer, at least in this diagram it does, so then you don't need that choice. But if you have more hidden layers, then you can do that. But you also want to keep in mind that you don't want your model to get too big, because one of the benefits of RNNs, as we'll go over in just a little bit, is that you can have them be relatively small, because this process of feeding in input from the previous layer actually adds a great deal of complexity, right? So we don't necessarily need our models to be all that big in order to encapsulate some pretty complex ideas. Any more questions? Okay. Now, so the pros and cons of RNNs. So one of the advantages of RNNs is that you can process input of any length, because you just keep passing it into the model one at a time. And you just keep passing in each input until you get to the end. And you can also see that no matter how big your input is, right, your model size is not actually increasing because you're passing in your input one at a time. And another benefit of this is that because you have time series data, right, or something where the previous input influences the next one, you can sort of encapsulate this relationship because that's encapsulated by this hidden layer right here. And so what you end up with is this idea of weights that are being shared across time, which means that whatever you influence, which means that the weight matrix that you multiply your previous hidden layer by is also going to apply to subsequent hidden layers. So you're sort of learning this generalized thing. One of the drawbacks is because you're passing in data one at a time, right? And what you end up with is relatively slow computation because you're not doing everything all at once. Another problem with this is that you're only passing in data from your previous layer into the next one, into the next one, into the next one. So this hidden layer doesn't actually encapsulate much data about previous layers, right? So what if you have data that's not just dependent on the previous time step, but 2 time steps ago, 3 time steps ago, 4 time steps ago, right? You might not know in advance how far back in time you need to go in order to figure out what hidden layers you need to pass in. So maybe you can think to yourself, okay, I'm gonna not only pass in my hidden layer from 1 round ago, but also 2 rounds ago, also 3 rounds ago. But you might not know how many rounds should you be doing that for. So that's a problem that persists, which is that you can't access information from a long time ago, so your memory is very short. And you also can't consider any future input, right? Because we're passing it in time order. And another problem is that because you're passing in these hidden layers one at a time, what you end up with is the vanishing gradient problem. Because as you keep passing in layers, right, as you keep passing your hidden input from one place to the next, that vanishing gradient starts to come in where you're passing it through the model multiple times. And as you keep scaling it and you keep passing it in, you're eventually going to hit a point where the model is not actually, where these hidden layers are not actually being changed all that much. So they're not truly reflective of what's going on.
Another thing is, if you remember, to train this model, we have to calculate the gradients, right? Instead of just doing this like matrix, our chain rule, when we do a backpropagation, instead of just doing it for the length or the number of layers for one model, we're doing it the start of the model, and then we're looping back again, doing it again to the same model. We're looping back again, doing it to the same model. Even if we have ReLU helping us, you can see how if we just keep doing this matrix multiplication, we may start losing information and we may start having magnitude issues of like basically the model the gradient either exploding in magnitude or being really small in magnitude.
Okay, so that's basically RNNs in a nutshell, right? Is that you have this concept of short-term memory, which is encapsulated by the hidden state, and that short-term memory gets passed from one input to the next, and that's how you end up reflecting the fact that this is time series data, where the past influences the future. Okay, so does anyone need a refresher on what vanishing gradient is? Okay, so just real quick with the vanishing gradient, the idea is that as you sort of let your outcomes explode to infinity, right? If you have some sort of activation function that kind of looks something like this, right? If you end up here, like somewhere over here, you can see that the derivative at this point is very nearly 0. And because the derivative is very nearly 0, that means that when we actually do backpropagation and we take a step in the loss landscape, we're not going to be taking very big steps. And because we're not doing that, we're not going to update our model very much, and it's gonna the process of updating is gonna slow down dramatically. So we're not gonna see that much improvement. Yeah, and even if for RNNs, even if we have ReLU, we can still encounter this problem because of the number of times that we're applying the matrix multiplication again and again and again. We can still end up in, say, the flat portion where, because ReLU looks something like this. Right, so if we end up somewhere here and we end up somewhere, can everyone see this? Yeah. If we end up somewhere here, like continuously after the matrix multiplication, again, we face the problem of vanishing gradients. Right. Yeah, so that would be the problem of vanishing gradients in a nutshell, and how it applies to RNNs specifically, and why it's more pertinent for RNNs even than it is for other neural networks, like the feed-forward neural networks and CNNs that we covered before. Okay. So to solve these problems, we have something called an LSTM. And these are a variant of neural net of RNNs, but they try to address that problem of that memory loss that we described before. And here to talk about it more will be Liu.
Okay, got it. All right. So now we'll be talking about long short-term memory module neural networks. The main difference between this and a recurrent neural network is essentially the memory stream that runs through the units as you input sequential data. So they are a type of RNN, but we include that memory stream inside the module so that we can solve some important issues. One issue is the vanishing gradient problem, which we talked about before. Yeah, one issue is the vanishing.
Yes, sorry about that.
So yeah, long short-term memory. So some of the pros of this type of neural network are that they don't solve it fully. For stacked LSTMs, you might actually have the issue of vanishing gradient, but they're much more effective at combating this issue than RNN. They also have long-term. They also solve the issue of like long-term memory problems because as we were talking about before. As we were talking about before, when you have RNNs and when you have long-term dependencies, say you have a paragraph or you have a like an essay that you want to put into the LSTM, and you put it through, and you put embedding by embedding through the neural network, you're going to face the issue of long-term dependencies, right? Because as you backpop through time, the gradients for the previous states are going to be sort of lower. So it's going to be harder to get those long-term dependencies between your word embeddings, and which you need, right? So if you have sequential data, you want to capture those long-term dependencies rather than only short-term dependencies. So that's what LSTMs help in combating. One of the cons is they cannot be easily parallelizable. And the reason for this is because they're RNN, and RNN, because of their recurrent nature, they're very hard to do all at once. Later on, we'll talk about transformers, which are parallelizable. So that becomes easier. That's one of the reasons why ChatGPT is possible. It's because it's so quick during training. And if we didn't talk about, I think they might have mentioned it, but one key thing to note is that LSTMs and RNNs are trained through backpropagation, but the type of backpropagation is different because in this case, you have a recurrent neural connection, right? So you can't just, you can't just backpropagate because you wouldn't take into account previous states. So what you do is you sort of unroll the neural network over time. And it's called backpropagation through time, something like BPTT, something like that. You guys want to Google it, it's pretty cool. And so that's the backpropagation technique you use. In backpropagation, so let's start. So this is the LSTM module. This is what we use. I know this kind of looks a little bit hectic because there's so many aspects of the diagram. It's kind of confusing, but it's actually really simple. The basic fundamental idea that we're getting into is you have a memory stream, right? A memory stream of all your previous data. So you have this stream sort of running through your neural network of all the previous things that you want, and you only add to the stream what the specific thing that you want from the previous data, right? Another aspect I want to highlight is when you see these two previous states, layers in your neural network, they're the same thing. This is just for previous sequences, right? So you take the output of one sequence and you input it into another into the output of the next sequence. And so it's sort of like this isn't an actual neural network going. This is over your sequence. So that's also one thing to note. Does anyone have any questions on we just talked about? Okay. So some key parts of an LSTM. One is its current input. You have an input, put it through the LSTM, then it has an output. Then you take the output of your LSTM, and now it's going to become one of the inputs to next run through your LSTM. In addition to that, you have a hidden state. This encodes the previous data, and this is just an output of the LSTM. It encodes the previous data that you had in your previous time step. And finally, the most important thing is your self state. This is what truly differentiates it from your RNN. This encodes the values of all previous inputs in some way. So it's essentially like it's like almost a summarization of all your previous inputs and the essential features of your previous inputs. And so yeah, these are some key parts of the LSTM and LSTM gates, right? So I like to think about the gates as sort of like valve, right? So you have information coming in, you sort of control the amount of information you let out rather than just letting out all of it. At the same time, some valves, they might direct the information like in sort of the correct manner. And you might add two different streams together and so on. So that's what the gates, that's the function that the gates serve. So the important gates that we have are, the first one is the forgot gate. So this computes what information you want to forget from the LSTM memory, from the cell state. That's the key. And the next gate is the store gate. So it computes what information you want to add for the LSTM memory. So you're basically asking, okay, I have this memory, right? I have this memory currently, and I have this input. So what do I want to update about my memory? What have I learned from this current input? That's what you're asking in the store gate. And the update gate, this just does exactly what it says. It just updates the memory. And then using the forgot and store values. And then the output just reduces the output based on the current input and the value of the cell state that you updated. And also your hidden state previously. So let's get into LSTM state. You can sort of think about an LSTM sort of like a conveyor belt. So on one hand, you have the memory of all your previous things. So you have your you have your experiences, right? So you have your experiences from all the previous inputs, and then you have the current input, right? And so all you're saying is, okay, how am I going to update my memory so that my experience, my memory is actually beneficial based on my experiences? And after that, you're going to take out, you're going to have an output based on that. And yeah, I mentioned that before. And then hidden state versus self state. You'll hear the words hidden state and self state quite often. The essential difference between the two is that self state is like that memory stream that goes through the LSTM, right? And hidden state contains important information from your previous state. So it's essentially the output of your LSTM from the previous time step, while self state is sort of like the summarization of all your inputs from all your time steps. So that's essentially the difference between the two. LSTM section. So let's get into it. So yeah, let's start with the forget gate. And what this does is it takes your hidden state from the previous input, and it takes your current input, like this is your current inputs. For example, say you have a sentence, hello, my name is, and you represent your words as word embedding. This is, for example, the first input would be hello, right? As a vector. And then in this case, you have you do is you take your current input and you take a previous hidden state, and then you put it to a linear layer. You put it to a P4 linear layer. And then after which you're gonna put it through this gate. Don't forget, sorry, we're not gonna reach that right now. But afterwards, you are gonna create your memory, which is right here, your cell state, and you're gonna put it with element-wise multiplication. But okay, we have both the inputs right now. We have the previous output, and based on what the previous is, we're gonna sort of filter out our previous. So all that this is doing is taking your previous input, your hidden state, it's getting your current input, right? And it's putting it through a linear. You guys can see it right now. This thing right here is your linear weight. This is your weight, and you multiply so you get this vector of your input in the previous hidden state. Right, so this is just the P4 neural network. That's what this signifies. And then you put your sigmoid function so that the values are between 0 and 1. So then this new value serves as a filter. So if it's 0, you're going to filter out everything. You're going to forget everything from the previous hidden state, right, from your in your cell state. And if it's 1, you're going to remember everything. So that's why we have this sigmoid activation function right here. Does anyone have any questions on this? you don't have it because you don't even have it. You don't have previous iteration, so you just start. Right? So, yeah.
How we update the weights? There are different input. I mean, how the weight is that a data and that workings?
Yeah, that's a really good question. So it's a little bit different because the thing is the weights actually shared. So the weights are shared over time. The variable parameters are shared. It's just that you have the recurrent connection. That means that you have to unroll the neural network over time, or in this case, over the sequential lifetime, the data. So you have to unroll the neural network. So that's how you update recurrent neural networks and LSTM. This is a problem actually because during the process of the neural, this can be quite inefficient. So it can mean what we call updating, gradient descent can be quite inefficient in this case. So it slows down your training time process. Great question. More questions? If this is confusing a little bit, if my explanation confusing you guys, don't be afraid of this. Like, this is really chill. Just need to like go at it again, and it starts to make sense. So yeah, this is just what the LSTM forget gate does. Like I said before, 1 keeps most of it, right? It keeps all of it, and 0 keeps forgets this completely. And this is like the reason that they made sigmoid activation function, the activation function for the forget gate, is because it sort of crunches up it maps your tensor to a value between 0 and 1, right? So that all the inputs, all the values of your tensor are between 0 and 1, right? And mathematically, this either keeps the same size of your value or it diminishes it in some way. That's what we need, right? We want to forget our tensor, a memory in some way. We want to forget all the non-essential parts and we want to remember the essential parts, the essential experiences. Does anyone have any questions on this? Like, okay. Now, right here, it's the store or the input gate. So it's called the input gate. And right here, what you're doing is you're essentially storing all the important information that you want into your cell state, right? So what you do is you take the previous output, the hidden state, you take the current input, and then you put them, the concatenated version, into a sigmoid function. And what this does is it, again, puts the tensor, all the values of the tensor between 0 and 1, right? And then you also put the concatenated values to another linear layer, and then this, in this case, the value of the linear layer will be between -1 and 1, right? Because we're using the hyperbolic tangents. And while the sigmoid function is sort of squeezed between 0 and 1, the hyperbolic tangent is squeezed between -1, -1 and 1. So what this helps us do is it sort of allows more flexibility. Because before we're handling the case where we had, per sigmoid, the values were between 0 and 1, so it sort of diminishes it. But with -1 and 1, you can add, and you can also subtract values. And we'll see why that's so important right here, during the addition phase. But all we're doing right now, the most important thing, is that we take the values of these 2 layers, and then we perform an element-wise multiplication of the 2 values, so that whatever we have at the end is what we want to remember and add to it. So this is the part where we actually say, okay, I have my input, I have my previous output. What do I want to remember from this, right? What's the meaningful experience I have, and what's the meaningful experience I want to extract from this? And so, yeah. And just to clarify, this thing right here, the CT, it sort of represents the candidate values of your new input, right? It's the values that you want to sort of diminish or take away from, and that you're going to have. So it's like the important experiences that you have. Does anyone have any questions on this? Yep. Which one?
Is that the way, or is that just like output that?
Yeah, so this is just the output of this, and this is just the output of the sigmoid. Yeah, that's just the output. And this thing right here, it like does element-wise multiplication. Okay. Good question. Yep.
Are both the weights like for INC like constant? Or is it just the weights for?
So they're not constant, they're the trainable parameters. This is. Yep, so this weight, and this phi, they're trainable. So that's what you train over time. Yeah, so this is your weight matrix for it. This diagram makes it a little bit complicated because it doesn't show that there's a linear layer right here. There is a linear layer. Like that's what trainable. That's what you train to change that.
Is that like different from the current where the weights are shared?
No, when we say the weights are shared over time, they're still trainable. It's just that they're shared over your time steps. So as you go through time, the weights are still the same. You can update, you still have to update those weights. So this is the same exact thing. They're shared over time, but you're going to update them. Okay. You have a question?
Yeah. I was thinking about that. Since we have finished the forget gate, why we still need a negative value for the tangent hypertangent function?
Yep, that's a good question. So all that the forget gate does is it forgets all the experiences, all the things from before that you don't need, based on what you have right now, right? And then once you forgot everything, you need some way to sort of like all the experiences that you have right now in your current input, right? And what tangent, like the parabolic tangent function allows you to do is it sort of allows you to either add or subtract. Do you see what I mean? Because the values are between -1 and 1. So it allows you to add or subtract from the previous number. So it allows you sort of more flexibility.
I mean, if diminished, so add here, I can definitely sort of understand why we need to add because we are inputting something. But why we need to also need to minus this?
Oh, so why do you need to manage from the cell state? Is that what you're saying?
Yeah, kind of.
I would say it's sort of because of, it gives you more flexibility. Because given a certain cell state, if you have negative values, you probably get a little bit of flexibility. That's a good question. Honestly.
You should remember that the values, like the numbers themselves, don't just have a human interpretable meaning, right? These numbers are reflective of some abstract quantity that we're looking for. So just because it's negative doesn't mean that we're forgetting per se. It just means that what we want to update it by is a negative number because we want the next number to have that amount of update. So the important thing to remember is that the new value of our cell state is going to be original value of cell state multiplied by how much we want to forget it, plus the current value of our restore gate times how much we want to remember. So you have those two components: original that you forget a little bit, and then your update times however much you want to remember. And that times however much you want to remember it is going to be reflective of the update you want to make, not necessarily.
So I think as far as you're saying, just because it's negative, it doesn't necessarily mean that.
It may mean that you remember less than
It's not that you're remembering less, you're just remembering a different number.
So now we have already explained the store, and yeah, this is an explanation of the previous. Yeah. Okay. So now to the update state. This is where we So this is where we update the value of our cell state using the value that we talked about previously, which is the FT right here, the forget base value, which is what L minus multiplication. The values are between 0 and 1. If either diminish it or keep it the same. And then the value that we had previously, which we produce an unemployed multiplication, and then we add it to the value of the cell state. So then we add our current experiences to the sort of like the stream of memory that we have. We use the equation, like the model physics saying that your tensor right here, you multiply it by the previous cell state. In this multiplication is element twice, so you take every single element and you multiply it by each other. And then you take the value of your IT and CP, you can use another unemployed multiplication and you add them. All that this is doing is because This is just adding or getting from the self state. That's going to be your new self state for the next round. So there's an extra recurrent relation.
D here is also translate or all this is cell cake.
With the CP?
Yeah, CT.
CT is your new self state value. So it's the new temperature that's going to be propagated to the next
I'm still a little
time state.
confused somehow. What's the difference between cell scale and the weight? Like the weight, yeah, the matrix W.
So that's a good question. So the weight of your matrix, that's your trainable parameter, right? So that's the thing that you can train. You can't train your self state, right? Because the self state is it's a tensor that's not trainable, and it's a tensor that's made based on the experiences that you have and the input that you have. So this is sort of a stream that goes through your LSTM over the time steps, right? But while your trainable parameters are which actually train and configure. Do you see what I mean? So it's like sort of like, say you have a stream, right, of water, when you have different valves. Your weights are the valves that you sort of like tighten or unscrew or so on to change how much water gets through. And the water is the self state. The water is the memory, essentially. You guys see what I'm saying? So the water is the memory that you have that you're gonna use to make further judgment. So yeah, it's still a tensor. It's still a tensor at the end of the day, but you don't change your self state because this also changes over time, while your weights don't change it. That's really good.
Why we need the previous cell gate? Because I think that because we have the hidden layer from the forget gate has already include the hidden layer even from the previous layer. Why we still need the cell gate?
Wait, can you repeat your question?
Sorry, but it's like let me see, because in your forget gate you actually had some information which is the pre-hidden layer, which like give the value to you. Why we here also need the cell gate.
So the cell gate isn't this, so it is from the previous layer, but it doesn't only have information from the previous layer. So the cell gate has information from all the layers. Because you have the current timestamp, and then you produce a cell state, and then this cell state can become a cell state for the next timestamp. Then you update the next time.
I kind of understand. Thank you.
So yeah, so you update it that way.
Just to add one thing real quick, this forget vector that we're learning here, this tells you how much you want to forget what you have currently, what you had before in your cell state. So you forget a little bit of what you had in your cell state, and then you add in what you learned.
Question. So the LSTM update, this just explains what happened previously. All we're doing is just we're updating the memory, the self state, and yep. And just remember that chain parameters are shared across all time steps. That's important to remember because it becomes really hard to visualize RNN sometimes because it has a different paradigm a little bit. We go. Then okay, and then the output. So this is the really interesting part, right? So once you've updated your self state and so on, now you have your input, your current input, you have your previous output, and then based on the new updated memory, you're going to make a judgment. And that judgment is going to be your next. That's going to be the next hidden state, right? Or it might not even be the next hidden state if this is the final layer in your LSTM. This might be the output. Okay? So think about the hidden state at the end as the output. So what you essentially do here is you take the previous hidden state, your previous output, your new input, and then you're going to put them in another neural network. Right? So you have another weight matrix. You concatenate the vectors along the dimension. You put those two vectors together. You add a bias, and it's your sigmoid function. Then you take your new cell state value. Then again, you put it to a hyperbolic tangent. This time you don't put it to a linear layer. You just put it to a hyperbolic tangent, and then you perform an element-wise multiplication, after which this new value will be the output. So yeah, this is the output, and then you take this and it's going to be the new hidden stage for the next. Like one thing I do want to mention is that this is exactly like how they work in real time. So if you go to PyTorch, I would encourage you guys to do it. And if you look at the parameters, you give these parameters to PyTorch and it gives you a model. Then you stack these models. PyTorch allows you to stack them, that one of them is after the other, after the other, after the other, after the other. And then so like, the power of these models increases drastically. Also, another thing that you guys might be wondering, right, is how do we input all our tokens at once? We don't in LSTM's case. We input the sequence one by one. And based on the different type of problems we have, suppose we have a classification problem, you're gonna only pick the finally outputted sequence, because you're gonna have multiple outputted sequences as you put in your input sequence. You're gonna pick only the final output sequence. And this is actually another reason why LSTMs are kind of weak a little bit, because they don't, for the initial set of outputted values, it might not be as accurate because they don't have as much context. Transformers are a good choice in this case. An LSTM output, yep. Does anyone have any questions on this? Here we go. Yep, that's a good question. So the forget gate is the forget gate sort of takes your previous output, takes your current input, and it's going to say, okay, what do I want to forget from my self state? So you're dealing with your self state in the forget, right? So you're dealing with your self state. So you want to sort of forget the experience that you don't want to have anymore. While for the output state, you're taking your current input and your previous input, and then you're saying, okay, based on these experiences, what is my output going to be? So you're not dealing with your self state. You don't deal with your self state. You're only dealing with the output of the actual state. Does that make sense?
Yeah, makes more sense. I'm still got it.
What part are you confusing?
I'm just confusing the exact role with every base. Okay.
We can probably talk if you're free.
Yeah.
Now we're going to come to transformers. 13. So important.
I need to see.
Oh,
Or advanced and embeddings. Which one? Whatever. Oh, it's not. Okay, I just HDMI is a or
I mean, if you can just join the Zoom call and just share your screen, or you can just also just put a copy into the drive.
yeah. Oh, it's done here.
Mm,
Right.
Here it is.
Nice. Yeah, okay. It's a little scuffed, but it's fine. It's good.
Let's make this a little bit better. Here? Oh wait, this is this it?
That's not it.
No. Okay, my bad.
That's it.
There we go.
Okay.
Okay, we are here. Transformers. What? Okay. There we go. There. Thank you. Transformers. Okay, this is like the thing. If you ever wanted, AI. Okay, here we go. That's a lot of stuff. Don't worry about it. Okay, so the idea. This is what we got. We got an input. We encode it. We pass that, and we get an output to the input. It's like, for example, this is called sequence to sequence. So we can use RNNs to do this. Like here, we can use RNN. Yeah. So let's look at this for example. We have our encoder. We pass the start word. We say I love learning, and then we do that, and we pass that. We get that final hidden state from the RNN, and we pass that as it's just a vector, right? We pass that vector then to another network. This is a separate RNN,
which we call our decoder. And our decoder pretty much takes that hidden state, and then at each step, its hidden state is then outputted, and then we're trying to pretty much predict an output word, and then we pass that along. We predict the next output word, and then finally, once it predicts the end word or token, we say to stop translating, right? So the idea is kind of like before, like we said, we're passing words into this recurrent model, right? And we could grab this hidden state at each of these points and just look at it. But for a task like sequence to sequence translation, like translating a sentence, what we want to do is pretty much pass in an entire sentence, and each time we're building up a richer representation of the sentence. So like right here, if we grab this probably only represent the word I. If we grab this could only represent the word I love, and this could only be learning. And then maybe if we get it here versus here, it would then be like a period, you know, and finally ended, or this would be like, maybe you could say, you know, it's just, we're trying to encode this sentence into a vector. This literally is a vector, that output hidden state. And then what we do is we pass that as the previous hidden state to our decoder. Our decoder takes in a subword, it takes in the representation of a sentence, right? And then we say, okay, I have this idea of I word, the concept and idea in a vector. And I have a word, the start word. And I'm like, okay, what word should I produce? And then we train the network so it does its best to produce the first word in the other language. And then we pass that hidden state along. Now remember, we have this could be like an LSTM. In the LSTM though, what could happen is we pass the sum, we pass the hidden, and what could erase from this hidden self state is like the word I'm we could get rid of I from this vector. So like this vector contains I love learning, kind of that like idea or concept, it's just some numbers, right? But once we pass it here, the hidden state will probably here no longer contain the information of I, because we just did the translation of that word. We pass it along again, we pass in this, okay, I need to say the words love learning, and the word Adam was the word we previously said. And we say, okay, what do we need to produce next? What's the next word in the translation task to do, right? So what we do is we just first L and then that word. Yeah, I don't know. Is this French? I think it's French. So it's Spanish? Oh. Yeah. Wow.
Yeah.
Oh, I'm wow. Okay. Well, yeah, and so that's like the basic idea is like you can use this for a lot of different tasks. This is translation. You could do this for stock prediction. Like here's the stock at this time, here's the stock at this time, here's the stock this time, this time, this time. Grab this vector and like then predict the word, right? Yeah, pretty much. Yeah, that's like the general idea is that we're pretty much like building up a representation of the sentence, and then we're decoding that as we go to do a translation. Now, the problem we've said this entire time with this is that this one vector right here at the very end, this hidden state, has to remember the entirety of the context of the sentence. Like this vector has to represent the entirety, yeah, and repeat, but yeah, it has to represent and contain everything in the sentence. The problem is that the context vector has to contain all of it. And if this is a really long sentence, as we said before, or a paragraph, this one vector has to contain all the information, and it makes it so the translation tasks become really hard for it to do. So again, this is the main motivation for what's called attention mechanism. So this is, we're almost at transformers, not really. So again, encode, context, decode, right? So the problem is this again has to contain everything. So crazy idea. Each of these has a hidden state. Remember I said like this first one could have, it's pretty much only encoding I, this one's encoding love, and this one's encoding learning. But like this one probably encode like I love learning, I love, right? These are all hidden states that are produced. It's just, we just don't care right here to grab those hidden states. But what the attention is the idea of what happens if we do, what happens if we pay attention to those hidden states. So they do have hidden states. What happens if we pay attention to them? So the idea is that at this last decoding concept, let's say, instead of just grabbing this vector that gets passed along the whole time, what happens if we let the network decide which hidden state we want to actually grab from? So it doesn't force this one measly little vector to contain all the information of the sentence. it lets it actually look at each of the words at the hidden state after they get decoded and say, which one do you want to look at? So this is what it looks like. This is for RNNs. This is the attention mechanism for RNNs. A little confusing, but yeah, it's okay. This is really confusing. Let's just look at the last. I think the last one is good. Yeah, the last step. Yeah. Wait. No. Let's just look at. Let's look at. Oh, let's look at the last step. Yeah. Sure. So look right here. This is our previous state. We still have to stay along in the decoding. But instead of just getting the context of the previous or something, what we actually do is we and bring it up here. And what this pretty much does is says, okay, based on what we said so far and what we want to say in the state, it combines it with all these other ones. Says, okay, pick which ones of these you want. How it does it is just through a feed-forward network, and it pretty much says, how much do I care about this hidden state? How much do I care about this hidden state? How much do I care about this hidden state? How much do I care about this hidden state? Right? And the idea is that you're paying attention to which hidden state you want, and then you're finalizing that, like whichever one you pick, as the context. Instead of just using, again, the context from the final one. Because again, this is just picking all of them, and just picking the last one to use as the hidden state. But attention mechanisms in RNNs is the idea of what happens if we let it look at it. To be honest, let's just use an example to make it a little clearer. Is it Spanish or is it French? I don't know. But for French, okay, this is French. We're right. Look at the word before. It directly cares the most about the meaning, right? If we look at words like let's look at the one that has like two. Like, was here, yeah, was kind of had those two. Because that like it gets translated into two words, right? So it actually, you can see that this word pays attention to this word, then this word, when it's decoded, still pay attention, right? So this idea of attention is pretty much the entire like basis of translation. So it's a little bit of like background, and you can actually see it right here. The agreement, right? The L, have really high tension with each other. And you can like some words have multiple. Yes. Okay. Attention. That's pretty much the idea. Yeah. Any questions? That was a lot. Wait. Sorry. Let me. Sorry. Say that again.
Well, if it was for training, very voice recording, and then whereas like it's also training and learning voice with the relevant place that very well.
I think what it does is it just has the same network like module here, and it pretty much just like this is a fixed before. Again, I don't know. Attention mechanisms are little. I don't know how they fully implement it, but I'm pretty sure it's just a normal feed forward, and they grab the hidden and they pass in one of these, and they say, okay, what's the like similarity like score between them? Like how much should I care about it? And it has to feed forward to get that value, and then it weights this hidden state by that value, and then it grabs the next hidden state and this, right? They can combine. You get a similarity score between how much do I this based off this hidden state, how much do I care about it? It combines them, and then it uses that score to then weight this. So this is pretty much just a weighted like attention of all these, right? It's like on the graph, it's like it really cared about one, but it's like it's a fixed network that sums over them. So it doesn't need like a network to look at all of them. It's just a network that can be compared to them. That makes sense. So the network pretty much just takes in the previous the hidden state, and the hidden state will decoding hidden state from the encoder, and then compares them, and then it just earns a for loop. I think, yeah, not too sure.
This is not that important because this is mostly motivation for the transformers. Did that answer the question, or kind of half? Yeah. Okay. Yeah. No, I just added this in the beginning because going straight to transformers is a little confusing. So, okay, this is the part I can explain way better, and it's gonna be way more clear, I think. Attention is all you need. This is the transformer paper. This is okay, like yeah, look at this, like 96,000 citations. That is insane for like research and papers. This is it. Again, very taunting, but we'll break it down. So self-attention, the main thing, and why I did the whole thing of RNNs and that idea of attention, because they have this idea called, literally the paper name is attention is all you need, right? And they introduced this idea called self-attention. So back to this, this is cool in that, okay, we don't have to have this long-term dependency. We can have it at any decoding time step. It can pay attention to what hidden state. But we still have this problem of, to get this hidden state right here, we still need to do the encoding, pass it along, do the encoding, pass it along, do the encoding, pass it along, right? We still need to get this last step right here, we still need to wait for this entire thing to process. So the entire transformer idea is what happens if we could have everything be attention, and we could even do what's called self-attention. So what happens if we could do the attention thing for words in the same sentence, right? If we could do this, that means that we don't have to wait for these previous time steps to be done to get this hidden state. We could just have this hidden state be a representation, which is a summed attention score of all of these, right? That's the idea. And that eliminates the whole problem what you're saying about needing that recursion. It's perfectly parallelizable, everything's independent. Yeah, so that's like why this blew up, because again, the parallelizability. So let's look at a word like it. So this isn't cross sentence. So we saw cross sentence. It's the same sentence, which is kind of the weird part. But again, it's self-attention. It's a big idea. Eliminate RNNs. Is that for the same sentence, we do attention on a word with other words, right? So like it, you can see it has a really strong connection with the word the, right? And I mean, it kind of makes sense. Like, it is referring to the, and those refer to the same things. So the idea is that we have every word, when it's getting encoded, be an encoding of the words that are closest to it, right? So that's that. Yeah, let's just look at a word. Let's look at a sentence like this, like on the river bank, right? We want to get a hidden representation state that is pretty much like an attention sum of all these different words, right? So, sure, we'll use this example. Remember, all these words are vectors, right? This is a vector, this is a vector, this is a vector, this is a vector, right? If we, for example, do the dot product of river, one, we go the same. If we do the dot product of, say, river and river, it's probably going to be a high score there, right? Let's see, do I have to have the scores? Yeah. So if we do river, we're going to get a really high score because river, pretty much same. You can get one. But if we do like river and bank, it might be less river, bank, and the river might have a higher score because the is referring to the river. On the river, maybe because on is that. So these are the actual vectors. Remember, we have word vectors in space, right? If they're closer together, they represent that they're closer in mean. Again, again, semantic. So what transformers do is try to encode this one vector river as a combination. There you go. A combination, a weighted combination of all the words based off how similar they are, right? This is the idea of self-attention. It kind of seems very basic here, to be honest. It's like you have all these words and all the vectors, and to pretty much like encode this word, all we're going to do is figure out how similar it is to all the other words, and then we're just going to normalize that, and then use them. So this all sums to one, and then create a new vector. This new vector is kind of the sum of the vectors which are closest in meaning to it, right? So to be honest, like if you look at it, 0.5, like the river is going to be most of the river vector at the end. but it's going to be some of the on, some of the, and some of the bank, right? And this is what pretty much like the idea of self-attention is doing is, I think of it as like saturating a single like vector, like it's a vector in space of representing river, but saturating the base of the other words around to create this like hidden representation. And you pretty much do this for every single vector. Now, can somebody spot a problem with this? What's the problem with this? Like, okay, we have the words in sentence. We want to now apply this thing called self-attention. We want to get similarity and encode word based off that and sum it based off like that. Okay, well, I just clicked it. There's no weights. This is just an algorithm. There's nothing being learned here, right? So the idea is that we pretty much are getting this word, like this is just an algorithm, right? There's no actual learned things in here. So to actually make this a neural network, what we add is we add what's called query. Yeah. So what we do is we just pretty much pass this vector here through matrix, like a really just linear layer called query layer, and it pretty much just transforms it. It's just some learned transformation. Why? Because then the neural network can just learn ways to manipulate it. But it's just giving the neural network a way to kind of like, I don't know, like actually have like it's just an algorithmic process, this kind of combination, but it allows it to learn how it wants to combine, right? So it can learn that, like, for example, I want to combine like nouns or something and like the person's like name or something. Or there, remember how we have the example, it would be what the thing is referring to. So it allows the network to learn what kind of attention it wants to do, right? With vectors in general, this algorithmic process, what it's doing is it's just combining vectors that are just similar in meaning. But what these matrices let you do, if you apply them to each of the vectors before dotting, and then when you use sum, it allows you to the network to learn how pairs to combine them, you know, based off different semantic meaning, if that kind of makes sense. Let's look at the actual math though. This is very hand wavy so far. Yeah, so think of this, like what, yeah, so this idea of query, key, and value. The idea is that we have like a query, like you're searching for something, like let's say we look up transformers, right? Our keys will be like the actual title, and our values will be the videos we're looking for, right? And if we go back here, what we pretty much did is we say we're looking at the word. Oh, yeah, I got rid of it. That's annoying. On the river bank. So this is river, right? We're looking at the word river. That's the query. We're querying river. Hey, you got the word river. This is the word we're looking at. And then we're looking at the keys. These are all the other words we have. We have the word of on and the river and the bank, right? And we're like, okay, here are my other things. And when we dot with them, we get a similarity, right? But what it allows us to do is matrix of query with key allows us to be like, okay, I'm querying for like subjects, and these guys can be like announcing, hey, I'm a subject, and then when you get the dot afterwards, it can represent the scores, and the scores can be representative not just of vector similarity space. These scores of, hey, how much this is the subject, or how much this is the pronoun of this. So it allows, again, these query, key, and value matrices allow it to learn different ways of that kind of similarity. But yeah, the actual math, you start with your vector, right? So let's say you just have a two-word like thinking and machine, and you just pass it through, again, just a weight matrix. This is, again, just to let it like learn something. And then you do that same thing for, you have another matrix called the matrix, which just transforms your vector embedding into this another one. And then you have your values, which does the exact same thing. It transforms it. Again, the whole point of this is just to make it learn, right? So then what we do is we get the first thing we're thinking, right? We get the query,
high with our key, right? So then that's our score. We're gonna have a really high score because the same words. But then we also grab the key value from the other one, and we get some years, right? And if we had another word, we also get another score. And then we score, we have it on the river thing, right? This is the similarity score after the fact. And then what we do is we use those, we normalize them, we make it so again they sum to 1. And then we pretty much just weight this vector by 0.5. You can't see it, it's a little faded out, but that's the point, is that we get 12% of the machine vector and 88% of the thinking vector, add them together, and that becomes your new hidden state, hidden representation encoded for that word, right? Yeah, that was a lot. Very hand wavy, intuition kind of stuff. Like the actual math is like, again, it's very weird at first why they do this, but any questions? Yeah. Like, is this making sense? Pull something, yeah.
Just for recap from what I understand.
Yeah.
You are choosing the former will use the dot product to match each of the inputs, and based on the dot product value, a weight is given to them, and then it's normalized. So my question is, how is the weight determined? It's not like in this cases where weights are like updated to the time, or you give some certain value to.
The weights are just learned through back propagation. Again, how you do it, there's a lot of derivatives and partial derivatives involved in math. But think of it as just, I think when first approaching a lot of networks, kind of nice to be, imagine there is some smart matrix that will do this nice thing for us, Like there is some matrix which it would do that, if that kind of makes sense. Like it's learned, yes. It's that is something, those are weights that are learned. Because yeah.
So it's like in your example, the value is the whole video, and the key is like the tags for that video.
Yeah, kind of. This is like, okay, this architecture just, okay, to be honest, this architecture just works. This process, if you want to think about it, is just working. Like all the things I'm saying and why I'm saying them so much, it sounds so like wordy about whatever. It's just because it's really hard to interpret why or how it works and the motivation behind it, right? Like I could just sit here and be like, okay, it grabs the two vectors, passes them through a matrix. That matrix then combines them, right? But like, if we want to think about it, it's kind of like the idea of querying whatever, like you're passing one through a query matrix, and it's like we'd like to think that it's transforming into a vector that's like shouting out, hey, I'm this word, and then you have all the other words pass through the key matrix, and they're saying, here's what I am, right? And then the query can go to each of them and each of the keys and say, okay, how much do I care about each of you? And then you now have values that you got with the querying keys, right? You have those values. And then you can use those values to say, okay, now you have another network, which is like transforming them to like, here's what my actual content is. And then you can sum those values based off those scores, right? That the query got from asking all the keys, hey, how relevant are you? How relevant are you? How relevant are you? Right? Yeah. It's like, that's the process though. The process is you pass each vector through key query value matrix to get other vectors. Again, sometimes they're smaller than the original, sometimes they're the same size. And then you do this thing of dot producting this one with every other one. And then you get that and you normalize it and you use that as a weighted sum for the values which were passed through the value net, right? That is the process, but kind of, again, the intuition is like, you're trying to figure out this word, how much does it relate to the other words, right? And then based off that, you have like how much you care about each word, and then you can like take, if I care about it a lot, I'm gonna take a large portion of it. I care about this word little, I'm gonna take a little bit of it. And then now my new word is a combination of the words around me. So I've kind of like saturated my word, and the hidden state is now like a combination of the words around me, right? Yeah.
Yeah. Anybody else kind of, just any question to clarify anything or any ideas? Yeah. Yeah.
So it's like, is this transformer fight as like the Fenton to like similarly like in place of it?
Yeah, so it does, if you actually really want to look at I have it in the beginning. Wait, did I? Oh, it's really far back. Yeah, so, oh well. Okay, yeah, so I want to talk about this part so far, which is just encoding it in a single sentence to get the hidden states, right? This is the encoder, this is the decoder, right? If you actually look back right here, again, encoder, decoder, you pass this like thing between them. This part of like the cross attention, I'll call it, I guess, does still happen. The difference is that to get these hidden states, it's not an RNN anymore. We're using self-attention to, instead of just passing the state up, we're saying to get this hidden state, we're going to do that thing of self-attention across all of them and like combinations to like make this hidden state, right? But the idea of this cross attention still happens by like through this, which I'll explain later, right? So the idea of the decoding words attending to the encoding hidden representations still happens. Is that, yeah. Okay. Any other? It's a lot. Yeah, okay. Feel free to interrupt anytime. This is like, again, like Transformers is a lot. It is a lot. So yeah, let's see a bit more. So yeah, this is kind of the idea. You're querying, you're getting similarity between them. This is the math. Again, like you could just look at this and then like, this is it. Like, I mean, this could be one slide and we could have all the math done and you know how transformers work. This math, you do this math, you implement this in PyTorch and you're done. But like, again, all this stuff is to build like a motivation for why we're doing it and how it actually is computing anything. Yeah, so again, you're just getting this, and this pretty much produces that that little like matrix of attention scores, but on the same words. So it then the softmax and normalizes all those values, and then you have the percentages of like how much you're going to care about each one, and you multiply it by the value. So then it grabs, you know, how much like 0.5 of this, 0.2 of this, 0. Whatever of this, and then it adds them all together to create this new vector C. Yeah, so remember I said like you have the query, you have the key, and you have the value, right? And that's going to be doing something. You can have another layer of, or another head, as they call it, of query, key, and values. So this is called multi-head attention. So we looked at this example, just one head. Remember I was saying like it's focused on what it referred to, but you can have multiple heads. Like that was just the orange head. That was like, I guess this is four-headed multi-head attention, and it's only the second head. This is looking at every head. So if you focus on, let's say, through the purple, and then for some reason it really cares about cross. That's what this head is focusing on. You can actually like look in some, you know, models and look at each head, and you can be like, oh, this head is doing what the articles are referring to, and this head is just the ones that are close to it, and this head is looking at something else, right? So the query key and values, they're for each head, they each have their own query key and value. So this is, let's say we have two heads. This is, we have a query key and value matrix in this first head. We have a query key value for a matrix for our second head. And what we do is we do the same thing for our first head. We do all that stuff, whatever, we turn the vector from this into this other vector, right? Into the two, how it's formatted. Let's say these are the words? Yeah, these are the words. So this is word one. Oh yeah, thinking, machines. And then thinking gets hidden, the hidden state is this, and then machines is the hidden state is this. But that's only after doing the process of wait for this first step, right? We can do that same process from before with these new set of query, key, and value matrices to get an encoding hidden state for thinking machines. These are different than like these encoding is different from this encoding. Because each head, again, corresponds to two separate sets of query, key, and value matrix. And again, the intuition of what it is doing with that is each head is like learning a different relationship. So like one query could be like, I'm like this, like noun, like I'm this noun, and then the key for that head, the key, like so this I'm this noun, key for that be like, here's the noun you should be looking for, and this is like I'm gonna like represent myself the best way of like the noun you're actually referring to, the person that noun is referring to. And this one could be like articles or like objects. What like here an object is the object you're looking for. And it could be like I am now an adjective. Adjective. And that would be like, okay, now it's like a combination of that, So again, each set of query key and value is kind of trying to take do attention and focus on different things, right? So we're trying to encode these words, but the encodings are different. The encoding from this to this, so 10 times 0 might be encoding thinking into like its representation of nouns. It want to be like it's like adjectives or descriptions of each of the words, So that's a bit more intuition. Does that make sense? Okay. Yeah. Anyone confused? Any? Yeah. This is like really hard, I think, again, I think the math is not the hard implementation. You can look it up and you can look at the math. Like again, this is the math right there. Oh, wait, did I skip past it? Yeah, this is the math, right? You just do this with another set of these each time for each head, and then you combine them and you're done, and that's transformer, and that's how you encoded it. But again, trying to understand like what they're doing is kind of important.
I would say the data we talked was after the ACM lecture on transformers, I like went back to my notes and spent a couple hours with the process of it and like making my own doc like with the information that was provided. So it would be if you have time, like go back when this is like no longer fresh and then go through this again and go through the slides and like figure it out that way, and that would really help.
Yeah. I would be insanely impressed if anybody got this on their first understanding. I think I spent like insane amount of time, like over like 6 months to a point. Like it's a long, it's very complicated. So yeah, this is just one more thing we have to account for though. Is that let's see if I can. Yeah, so you're pretty much explain it this way. Yeah, I'll explain it like this. You're pretty much getting this list of vectors, and then you're outputting like another list of vectors. Right? The problem is, again, you can put in a single head, equal values, right? But if you do multi-head, you have a list of n heads. Here we have set of values, second set, third set. When you do the output, you actually have multiple sets of output vectors, right? Because you have this one is from the first head, second head, third head, all the way to the 10th head or whatever, right? And the problem is, before, what we could do is we can actually grab this from here, we pass it in here, and we can use it back in the head. We could run this head over and over and over. The problem is with multi-head, you can't. You could maybe run per head over and over, but what we want is after all the heads process, you run this through and you run through the first head, grab this, second head, grab this, third head. You get all these heads. You actually want to concatenate them, then just add them into a long vector, and then do a linear projection back in the same size as the original. This just allows us so we can chain multi-head attention together over and over, right? It's like for one iteration, we could have the head of like nouns and the head of adjectives, and then they all get their consensus of how I've included all the words in hidden state, and then you say, okay, now just put them into a better representation. That's the sum of adjectives and nouns after that. This is just again little details. You've learned this part. This is it now. You pass the input here. You have the query, key, and value. You do the multi-head attention. You add a norm. For now, this is the residual connection.
We can put that later. But pretty much you pass it through, then you pass through the P4, which condenses it, and then you can pass it back. So again, you have this multi-head attention. This is what the multi-head attention looks like. You have the query, key, and value. You have each one of these are literally just a linear layer that transforms the vector into something else. You do that scale dot product attention. But again, it's the dot product of the query key and values to get the similarity, and then those are used as weights to then sum the values, and then you concatenate all those together to then get a linear projection. So yeah, one little thing, yeah, that's like the bulk. It's the self-attention part. That's, again, I think really confusing. Ask me after, or you know, spend time on it. It's a lot, okay? It's a lot. Any questions? Again, or they're not going to help. Yeah, maybe they won't help. It's a lot. Okay, continuing on. I think we have to check through. One thing that we kind of forgot about and we kind of need now is what's called positional embeddings. So yeah, the thing with RNNs is like they unraveled, right? And what they implicitly did was they kept like kind of like a track in the brain of time, right? They could encode like, oh, I'm the next one, I'm the next one, because in the hidden state probably like have a built representation. The idea, the point being that with transformers, there's no difference if you switch the order of any of the words. Again, wow, this presentation is bad, not good. Wow, this presentation is good, not bad. Like, it doesn't matter. The word bad would have its attention towards all of these. The word good would have its attention towards all of these. And then you just get a list where the vectors are just swapped in order. It wouldn't encode them any different if words are swapped, which is bad. We want it to, when it produces a hidden state, when it gets passed in the value, we want it to have a different meaning and vector or hidden representation if words are swapped, because word swapping changes the sentence a lot. So we have to our vectors that we're passing through, we have to add to them what's called positional embedding. So let's say we had, it's the first word, on the river bank, right? We want to add some kind of thing to this vector to give it a richer representation of where it is in the sentence. And this is kind of the idea behind positional embedding, because again, unlike RNNs, we don't have an implicit idea of where we are in the sentence. So, I mean, one way you could just like add the index, right? So the 30th word, just add a 30 vector, but this like demolishes the entire semantic similarity all these vectors have. And these are really constructed in a way where you can be like, things clean, add it, have really nice rich representation. But if you add this is like garbage in that, killing it. So you know, we could normalize it maybe so that it doesn't include the magnitude and you have one. Still, that this vector is really good in that one in the space might be something that doesn't really make sense position-wise. What the authors of Attention Is All You Need and the Transformers, they decided to use pretty much sign functions. And they used this is how they did it. Yeah, they pretty much does anyone know what Fourier series are? Yeah, okay, that's a decent amount. What we can do is we can have the first value in the vector be its position. So let's say it's like index of 0. You have a really high frequency signals value. Then we can do for the second value in the vector, we can add a lower frequency and a lower frequency. And then just put it just really nicely without ruining that semantic world that those vectors exist in of similarity, clean, clean, all that. It can still encode position without ruining that kind of semantic meaning in that vector space. So yeah, this is positional. Yeah, that's pretty much what you do. So imagine like the stick index, you can you know, 1 for the first, 1 again, and then maybe put that. Yeah, so that's what you do. With 1, you just pass it through, and again, it's something high frequency, lower frequency, lower frequency, lower frequency. Do 48 like index of all of them.
if that makes sense. More visuals, again, a lot of math. If the idea of kind of like just decomposing a signal into like increasing frequencies kind of makes sense, then that's kind of what we're doing. Yeah.
For the sine function, are we like changing the frequency of x inside the sine function to actually indicate the position?
So what we're doing is we're adding to each of these vectors. So these are vectors like on the river bank, right? Yeah. We're adding another vector to encode position, right? We're trying to figure out what vector we add here. What they decided upon is the vector that you should add is a vector where that the first value in all of these vectors should be a really high frequency time function, right? And the next value in the vector should be a lower frequency corresponding to that index, if that makes sense. Yeah, that kind of, so like, I'll go back to this image. So if we're saying, okay, the zeroth vector, the zeroth word, what do we add? We add, let's go next one actually. We'd add, for 0, we'd add these values, right? So do this, and then probably even more. Does that make sense? So let's say our vector is only size 3, we do that. But if it's size like 100, like a word vector, then we just have everyone decrease frequencies. Does that kind of make sense?
Kind of makes sense.
Yeah. So like again, yeah, you just pretty much pick this index. You look, okay, first column is going to be that. Second's going to be that, or third row. Yeah. So the vector is going to be like 0, 0.9, 0.5. And the next one will be, whatever that is. You're just sampling from different frequencies of time functions. It works. This is what they do. Yeah. Again, I think the intuition is if you can think of Fourier series, you're decomposing any signal or any position in this case into just like some like doubling frequencies, Yeah. Okay. That's what it looks like visually as well. Okay. Yeah. I don't know. I'll fast forward really fast. You pretty much understand it. There's residual in that thing going on, but again, everything we kind of understand before. We do some positional embedding for all this. We pass it to the self-attention and it encodes it. How does it encode it? It does this kind of like similarity culmination and then passes it through. Yeah, let's ignore that. Let's ignore that too. Decoder. Decoder. So the one thing we just ignored, I'll go fast. The one thing we ignored is that let's say we're like decoding and we have an entire word. Like let's say we're looking at this word here. This word here, it will look at this word ahead. So what we do is, let's say we're decoding this word, we pretty much math and say you can't look at the one word because it's decoding. If it did, we treat it like that. Then actual inference, if you like trying to look ahead and there's nothing there, and then you're complaining and things will mess up. So yeah, look, yeah, there we go. Robots must obey orders. It can't look ahead. It's masks the words ahead, even though orders could be the next word. Here's a little diagram of how that kind of works. The encoder can look at it. The encoder you can do however you want. This word can look at this word really carry encoding. But when we keep coding, we have that kind of sequence thing, and that's after past inference. Yeah. Okay, should have timed it better. Same visual. Teacher forcing, let's ignore that. Why do they do so well? So this entire thing I said about self-attention isn't even that great of a thing. We learned that you can replace the self-attention thing with like averaging all of the ones around you, and it still does well. So like self-attention is still used, but again, it's this idea of you're saturating this token. The abstraction we realize is the main thing which makes transformers good is the idea of mixing. You're getting this word and you're saturating and mixing it with the words around it. And the scheme we do it by is this thing called self-attention, dot product, and clarity evaluation. But what they learned is that we do averaging, and then that's good enough. Like it hits 90 performance of transformers, which is kind of crazy. So self-attention is good, it's still used, but
the main idea and the main intuition I think you should take away from all this is that when you're encoding a word in a sentence and getting generalization, you're saturating with all ones around it. It performs better than baselines and other things. Here are more stuff. Vision transformers are just a thing. You can treat tackles as an image in words and have that same situation be included into massive prediction in the class. So these don't have to be words in an RNN. They can even be packaged of images. And again, this performs better than baseline. This transformer idea of like saturating the individual ones around it and combining them and then doing an output is just surprisingly really good. Yeah, we patch because there's a lot of pixels.
That's the thing about encoder decoders. So we usually use only an encoder decoder architecture if we're doing, say, a task such as translation, where we have, say, some sort of we're mapping some input sequence to output sequence, and the input and output sequence have like slightly different distribution. When we're say just using like ChatGPT, for example, where our goal is just to say predict what the next word is, or predict what the next token is, because that's basically what ChatGPT is doing. Like if you see the ChatGPT like they're like slowly generating word, it's not just doing that because it looks cool that it is slowly generating character by character sentences. That's how it actually works. That's how it's generating one token at a time. We basically use something called a decoder stack, which is basically the idea of like you're basically auto-completing by feeding what was already out of the decoder back into itself, almost kind of like an RNN. But yeah. So with things like ChatGPT and stuff like that is why it is just decoder stacks. And encoder where you have a much more sort of like paired data, like in translation tasks. You have one input sentence corresponds to one output sentence, instead of in decoders where it's just like you have a bunch of data and you're trying to kind of use your model to approximate the distribution of all text as it has been. If that makes sense.
Yeah, for like abstract representation for language. Back in the day, we handled the language space embedded in that space, so abstract vector space. Then we make that abstract vector space, then we keep the limits. So that's why it's need to put.
Yeah. It's so okay. Like a lot of modern deep learning, is things that we don't entirely understand why they work. It is built from a lot of ideas that people have came up with before, and like the transformer didn't come out of nowhere, right? It is based on papers and ideas that came before. Like you can kind of see some similarity between transformers and LSTMs, for example. Yeah. Like so like these don't exist in the vacuum. But a lot of this we don't like even the best machine learning scientists don't have a concrete idea of like extremely certain idea about why they work. For example, like I was talking about before, like we still don't really know why resonance work. There's a lot of theories out there, a lot of different explanations. There's a lot of experiments that support certain theories over others, but we still don't know why it works so well. And that's kind of part of the fun of deep learning, is that sometimes you see a paper and you just go, wait, that works? And they're like, yeah, it works. And you're like, okay, I guess my entire understanding of this thing was not very correct to begin with. But that's, yeah. Speaking of modern deep learning, that is what we're going to be covering next time. But by the way, if you look at the slides, here are some links that explain transformers pretty well, I think. And modern deep learning. So this is basically what next time we're going to be covering. You might be like, what topic are we actually going to be covering for modern deep learning? That's a good point, because we want part of it is that we want you to also recommend topics that you want to know about, and we do have officers. We probably have an officer in ACM AI who is good at this topic. Some of the topics that we have been throwing out so far include these. I will definitely be talking about some sort of generative prediction. I'll be talking about various coders, generative adversarial networks, which is actually what currently projects you're working on, and diffusion models and good and like image text understanding. We're going to talk about things like transfer computation and stuff like that. We're going to also touch on reinforcement learning, which is basically going to be a super fast speed run of our week 2 reading group taught by John Zhang. We may or may not get him to be here in person. We will see. We will also quickly cover large language models in the current landscape of what they are like today. And also we may talk, if we have time, a little bit more about transformers if I force it. But if you have any other topic that you are potentially interested in, just let us know. If you have, because the next workshop, the last workshop, is going to be after Thanksgiving at week 9 Wednesday. We have a bit of time to prep this, so if you have any ideas, just come up to us in person, say, hey, I want you guys to cover this, or just let us know in Discord and all the other ways to reach us. Thanks for coming today. Hope to see you in 2 weeks.